Weather lesson number 4 is all about Doppler radar. And that's it. Right there, that's a Doppler radar. It looks like a giant golf ball sitting on top of a tower. Well, I am at the main NexRad that we use in North Little Rock by the North Little Rock Airport. And I'm going to talk all about that because it's us in the Channel 7 the weather team in the Channel 7 Weather Center that analyzes data coming from that. That data goes into your weather app to interactive radar. It goes into the weather center. And that's why we say Doppler radar indicates tornadoes or a tornado or straight line winds, or Doppler radar indicates large hail. That's it. That's what we use. And I'm going to tell you all about that, what exactly that is. That's, again, a tower. And inside that's called a radome. That big white thing looks like a golf ball. It's called a radome. And it looks like a golf ball. Inside is an antenna spinning around, scanning the skies of Arkansas. There are so many of these all over the United States, but there aren't enough. And I'll show you that in just a second. What does, I hope this comes up. What does radar stand for? Did you know that it stands for radio detection and ranging? Radio detection and ranging. That's what radar stands for. There it is, our live Doppler network. We're scanning the skies. We're using the National Weather Service Doppler radar in Memphis. Here in Little Rock, you see that one scanning around. In Fort Smith, Shreveport, and Jackson, we use 5 radars to analyze storms, and we were doing this yesterday as those big storms went right through Arkansas. Now, right on top of that radar, where I'm located right now, near the North Little Rock Airport, right over that, you may have heard the term used in the movie Twister, the cone of silence. They did not use the term correctly. The cone of silence is the area directly above the Doppler radar. Since the radar beam, you see there going out, scanning through, right over my head right now, it can't see above it. And because of that, there's a little hole, a little donut hole. And that's called the cone of silence. It's an up-close look. That's the Doppler radar scanning right behind me as seen from our live Doppler network. Radar has limitations. It is a wonderful tool, but it is not perfect. If you live in central Arkansas, you have fantastic radar coverage, and nothing can ever beat a pair of eyes, storm chasers, trained storm spotters. Nothing can ever beat that. But there are limitations to the Doppler radar, and this is a huge problem that we've had to deal with for a long time, especially over southeast Arkansas. You have to understand that there's the curvature of the earth. So as the radar beam from this Doppler radar behind me, as the radar beam shoots out towards southeast Arkansas, because of the curvature of the earth, it increases the radar beam, the detection, increases in elevation due to that curvature. So there are times in southeast Arkansas, even northeast Arkansas, away from the radar, and even southwest Arkansas. Because of the curvature of the earth, sometimes we can't see where the tornadoes are, and they go undetected. Now, this typically doesn't occur to the big tornadoes that can be detected at a greater altitude, greater height, but the smaller ones can often go undetected. I've been asking for a new radar in southeast Arkansas to give you better protection, but that goes back to government resources. But we use this one primarily, and that's one of the limitations that we have. That's why we rely so much on your weather reports coming to us on social media, going to the National Weather Service office, letting them know if there's anything that the radar might be missing, because it does have its limitations. Don't worry, I've got more coming here. Not that. So here's the NexRad radar coverage. Look at all the NexRads around the United States. And what you see in the yellow, that's areas that it covers up to 4,000 feet. Anything above that in the orange, 6,000 feet. That's the coverage. And then 10,000 feet. Let's look a little bit further into Arkansas, and you can see great coverage around the NexRad here in Little Rock. Great coverage there. Fort Smith, you got Memphis, you got Jackson, you got Shreveport. But there's a radar hole right there over southeast Arkansas. And it would be fantastic if we had a NexRad radar somewhere around Star City or Monticello. Right now, as far as I know, we're the only TV station that has access to use on television the ULM radar. the University of Louisiana Monroe, the only station in Arkansas or in the Little Rock market that has access to show on TV the University of Louisiana Monroe, and we can actually have a little better view of what's going on in southeast Arkansas. So that has helped quite a bit, but it doesn't do what we need it to do in some of the severe weather situations. So it would be fantastic if we could get a radar, the government to put one here in southeast Arkansas and one in northeast Arkansas. It would help us out tremendously. Now, there's a video presentation that I want to show you.
It used to be that you could only warn one person about a tornado after it had already blown down someone else's barn.
Now, on average, we're able to issue a tornado warning 15 minutes before the tornado's even there, and that wouldn't be happening without Doppler radar.
This NexRad system has reduced fatalities on the order of 45% due to tornadoes since its advent.
We have a lot more information now about storms and being able to understand how they develop, how they produce severe weather, and how that information might be used to improve warnings for our National Weather Service partners.
The lab is unique in that we serve the nation by supporting the National Weather Service in its mission to protect lives and save property by improving the accuracy and the lead time of severe weather warnings.
We have a legacy of radar research and converting existing technology from military to weather purposes.
A recycled Doppler radar led to the development of NexRad, installed nationwide in the early 90s. It allowed forecasters to see storms like never before.
Not only did we help bring that technology to the National Weather Service and to help protect lives and property, but we have continued to upgrade that technology, keep it relevant, and keep it state-of-the-art.
Recently, a major upgrade was added. Dual polarization technology takes the radar from 2D to 3D. Forecasters now know more about what type of precipitation is falling, which is very helpful during winter storms, as well as how much rain is accumulating, resulting in better flash flood warnings. The radar can also detect and track tornadoes based on debris. Looking to the future, the National Severe Storms Lab is testing the capabilities of phased array radar. Originally used by the U.S. Navy, the antenna scans the skies electronically rather than mechanically, allowing the radar to focus on a storm.
With current technology, we get a full picture or image of what is going on within a storm every 4 to 5 minutes. So it's more like a snapshot. Whereas with phased array radar, we get that picture of what's going on in the storm every minute, so it becomes more like watching a movie. So we can do adaptive, rapid scanning on the storms that matter most, being able to provide the information that's most relevant when and where it's happening.
Another advantage of phased array radar is its multifunction capability, providing weather and air traffic information simultaneously.
Number one, it is a system that promises to replace and expand upon the existing weather surveillance radars. Secondly, to replace aging air traffic surveillance radars. And number three, it offers a potential application to meet Department of Homeland Security and defense requirements for identifying and tracking non-cooperative aircraft. With the replacement of all these various radars with a single system, the American taxpayer could realize substantial savings in cost.
You have a lot fewer radars to maintain, and the electronic capability of this also reduces maintenance costs because you do not have moving parts.
Not too long ago, the ability to predict severe weather was thought to be impossible. During the past several decades, research conducted at the National Severe Storms Lab has developed life-saving tools like Doppler radar. We've progressed from no warning of threatening weather to about a 15-minute lead time, and current research promises to extend that much further.
Our knowledge of severe storms and how they behave, and our use and ability to use the Doppler radar technology is in a lot of cases a direct result of that close working relationship, that research to operations component that we get between the National Severe Storms Laboratory and a forecast office.
That history and understanding of how these data can be used by our users and doing the research to help advance the use of radar technology, really it's what we live for, it's in our lifeblood, it's in our history.
And so that's all about phased array radar and the radar that you see right behind me. And that's from the National Severe Storms Laboratory. They have a fantastic site for teachers about the resources with that. So one day we're hoping that that radar will be replaced by phased array. And several years ago, I had the opportunity to actually stand inside a phased array radar. Of course, with it off, if it was on, I would have been fried. But I got to stand inside of the phased array radar in Norman, Oklahoma, and it's fascinating. I cannot remember the specifics, but there's these little tiles, and each one of those tiles is equivalent to like thousands of microwave ovens. It's a lot of energy. It sends out, and we get a real-time look at the storms. As it is right now, this is a fantastic tool, but they're getting outdated. We need more of them to cover up those radar holes that I said, like we have in southeast Arkansas, to help warn you. But one day, hopefully, we're going to have phased array. Now, when we have severe, hopefully in our lifetime, but when there's severe weather, typically what happens is that scan that's going around inside that dome, it takes a few minutes to tilt at about half a degree, and then it keeps tilting up and up and up, and then it sends all that stuff out, all that data out to the TV stations and to the National Weather Service and everybody, and it takes about 4 or 5 minutes to do so. But when there's severe weather, like we had Sunday night, it will get an image every minute or so, maybe even a little bit less, of one scan at the very base elevation, at that half a degree scan, and send it out. So we're getting data pretty quickly, and it's extremely helpful. But phased array would solve the problem and get it to us instantaneously and almost in real time, which would go a long ways to helping save lives and property. And eventually, that radar system is going to have to be replaced. Just will it happen in our lifetime? Does anybody have any questions? Again, this is going to be posted at the Arkansas Weather blog. Gene says, thank you, Todd. This is all very interesting. Yeah, I mean, this NexRad radar, I was actually at the commissioning ceremony for the very first NexRad radar in Norman, Oklahoma back in 1992. The first one that was commissioned, I believe it was 92. I got to attend that. Here's a question. How can you get more Doppler radars and then get the ones we have updated? Well, these Doppler radars, the towers that they sit on, and then the actual radar, and then you see the buildings. You may be able to see the buildings down here. All that is enormously expensive, in the millions upon millions of dollars. And then the cost to maintain those radars also adds up. So it's a huge expense, and it's taxpayer funded. So that obviously is where you're going to have the holdup in that and funding that. But thankfully, we do have a great radar system. But at some point, it's going to have to be upgraded and updated. And like I said, I hope it's in our lifetime. And I wish that we could get one more of these. There's already so many across the United States. I showed you a picture. There's well north of 100, I believe. But there needs to be one in southeast Arkansas for better coverage. There's a hole there. And it's very difficult to detect the smaller tornadoes. The big tornadoes that show up well all the way up into the sky, those are fairly easy to detect. The big ones like we had in southern Mississippi yesterday. But when you're talking about the smaller tornadoes that don't happen but just in the blink of an eye, it's a lot tougher to see those when you have a radar so far away. All right. I've got to get back home to do Good Afternoon Arkansas at 3 o'clock. And I want to thank everybody again for watching and for attending weather lesson number 4. I'll answer this question. Another round of storms coming tonight? No. As a matter of fact, there could be snow in the mountains of northern Arkansas. I'm not kidding you. Little to no accumulation. No severe weather in the forecast this week, for the rest of this week. How high up can the Doppler radar tell weather? Well, again, because of the curvature of the Earth, you can go back and watch this video. Because of the curvature of the Earth, it sends out a beam, and it can go up, southeast Arkansas. We're probably shooting at about 10,000 feet at least in elevation. Obviously, here we're right off the surface, but the further out you go, the further that beam gets above the surface. That's why we need another one. I did a story as well out in Oklahoma many years ago that they were, I don't know where the project stands right now, but they were putting smaller radars on cell towers all over the state. So they were smaller radars to get better coverage. I don't know where that project stands. I believe it was Project CASA or CASA or something like that. I'm not quite sure. How can you see debris on radar? Well, with dual polarization, an upgrade to these radars that we had a few years ago, it sends a beam out horizontally and vertically. And it can tell when it hits the target, when the beam hits these targets way out into the atmosphere, it can see the size of them. And it processes that data, the size of the objects. And if we see irregular sized objects in a small area, we get what's called a correlation coefficient dropout. And we can see through the colorization and color palettes that we have to interpret all that data, the different size objects, which could be limbs, trees, cars, pieces of homes, and we see that there are objects of different size. Now, rainfall, the water droplets are fairly uniform, so we would be able to see a smoother area of uniform sized objects. But when you talk about debris, sometimes, and like we saw yesterday in southern Mississippi, you see what are called CC dropouts. And that's when we knew that there was debris being thrown up into the air. And there's been a lot of research that shows that when we detect the debris at a certain level in the atmosphere above 15 or 18,000 feet, we know we're getting the power of a tornado of around EF4 or EF5 that can loft it up to 18 to 20,000 feet up to the atmosphere. So there's a chance that that tornado in southern Mississippi will be in a 4 or 5, probably a 4. All right. I hope everybody stays safe. No severe weather this week. We're done with it for a little while. Tonight we're tracking the potential for light rain and light sleet and light snow, especially northern Arkansas. Thank you very much for trusting us at Channel 7, the team with the most experience.